Hello, everybody. So, this is my lecture for week 11, session 1. We already discussed chapter 6. If you remember, we discussed three main topics in this chapter. The first one is the second law of thermodynamics. The second topic, we learned some cycles, the heat pump, refrigerators, and heat engines. And then the third part, which is my today lecture topic, is the Carnot cycle. So before we go over the Carnot cycle, let's just go over the previous lectures. So if you remember, for all cycles, we can prove that the first thermodynamic law is Q net equals to the W net. And if you start from the first thermodynamic law, you can simply prove this equation. So for all cycles, you can write Q net equals to W net. Then we discussed the heat engines. So if you remember, guys, heat engines are devices that convert Q to W. So if you remember, for this actually, cycles for the heat engines, we have four steps. The first step is, heat is absorbed from source, and then what happened? There is a boiler. In this boiler, the inlet is normally compressed liquid, and then this compressed liquid is converted to the superheated vapor. And then this superheated vapor goes through a turbine, and then a part of this fluid energy is extracted, and then W actually net is the product or the outlet of this turbine. And then the exit of this turbine normally is saturated vapor, saturated liquid mixture, and then this mixture goes through a condenser, and then heat is transferred from this condenser to the energy sink, and then the exit of this condenser is normally compressed or saturated liquid. So this is the concept of heat engines. Based on the definition of thermal efficiency, we can write the efficiency. Actually, the general definition for efficiency is desired output over required input. In this case, for the heat engine, the desired output is W, and the required input is Q in or QH. If you just use the substitute for the W net from the energy balance for cycles, you can prove that the thermal efficiency of heat engine can be determined from this equation. So you have two equations to calculate the thermal efficiency of heat engines. Also, we discussed the first statement, or the Kelvin-Planck statement, for the second law of thermodynamics. Based on the second law of thermodynamics, actually it's impossible to have the any heat engines with a thermal efficiency of 100%, or it's impossible for any device that operates on a cycle and receive heat from a single reservoir and produce a net amount of heat. And sorry. Then we discussed the refrigerators. If you remember, normally heat is transferred from a medium with higher temperature to the lower temperature. If you want to transfer heat from places with lower temperature to the higher one, we need to use a refrigeration cycle. For the refrigerators, normally we have four different steps. So the first step, heat is absorbed from a refrigerated space or from heat sink. And then there is an evaporator. In this evaporator, working fluid actually converts to the at constant temperature and pressure, convert to the saturated vapor. And then there is a compressor. In this compressor, actually fluid is compressed, and then both temperature and pressure of this working fluid increases. Now the temperature of this working fluid is higher than the surrounding or the room temperature, and then heat can be transferred from this fluid to the surrounding. So at constant pressure, heat is transferred from condenser actually to the surrounding, and then there is expansion valve, and fluid again return to the evaporator. If you want to calculate the COP, the coefficient of performance of this actually refrigerator, you can divide the desired output, which is QL, over required input, which is W net. So it's possible to show that the COP of refrigerator can be determined from one of these two correlation. Let's watch this short actually video that shows the different parts of refrigeration cycle.
Refrigerators are an invention of the 20th century. In medieval times, long distances had to be traveled in order to get ice and snow to keep food fresh. All modern fridges with a compressor work in the same way. A container made of plastic and metal is equipped with several insulation units so that ambient heat cannot get into the fridge. A thermostat measures the temperature in the fridge. It is linked to the compressor by a cable. Tubes with a refrigerant in them are connected to the compressor. The tubes are grouped into the evaporator unit and the condenser unit. Evaporator and condenser are connected to each other through a throttling device, such as a tube with a very small diameter. Normally, food placed into the fridge has a temperature above 10 degrees Celsius, and that's exactly where the fridge gets warm. So this heat has to be transferred back into the environment. Heat transfer into the environment is done by the refrigerant such as isobutane. Before we start examining the whole process, we should talk about three very important principles. The first principle is called latent heat, which occurs at a phase transition, such as water boiling or ice melting. Latent is Latin and means to lie hidden. That is, the refrigerant will absorb heat but won't get any warmer because the heat is stored as internal energy within the refrigerant.
So look guys, actually you know that there are two mistakes in this graph. The first thing is that in this area we have saturated mixture, saturated liquid, saturated vapor, but not the liquid. Liquid is in this area. And then the second mistake is this part. We have vapor here, but not gas. We already discussed the difference between gas and vapor.
The second important principle is the fact that two bodies that are in thermal contact move towards thermal equilibrium. That is, the hot body gets colder and the cold body gets hotter until both bodies have the same temperature. The third principle is the relationship between pressure and temperature. According to Emonton's law, the pressure of a gas is directly proportional to the temperature. That is, the higher the pressure, the higher the temperature. Now, let's talk about the vapor compression cycle. In the condenser, the refrigerant is under high pressure and present in liquid form. The refrigerant has to pass a throttling device to get to the evaporator. Here, the throttling device will produce a substantial reduction in pressure. Consequently, the refrigerant cools down and partially evaporates. The other part of the refrigerant remains in liquid form. The refrigerant flows through the evaporator within the fridge. Now, thermal equilibrium between the inside of the fridge and the evaporator takes place. As a result, the heat is transferred to the evaporator and the fridge becomes cold. While absorbing heat from the fridge, the refrigerant evaporates but doesn't get much warmer because the heat is stored as internal energy within the refrigerant. The compressor is installed at the other end of the evaporator. This compressor will push the refrigerant under high pressure into the condenser. As mentioned before, this will increase the temperature of the refrigerant because pressure is directly proportional to temperature. This heat is transferred to the environment because thermoequilibrium between the condenser and the environment takes place. The release of heat causes the refrigerant to liquefy. From here, the vapor compression cycle starts again.
Okay, guys, this is the concept of, refrigerator. And then the last actually cycle that we discussed, my previous lecture, was heat pump. Heat pump has the same concept as a refrigerator. Actually, heat pump used to transfer heat from a lower temperature medium to the higher one. So they have both heat pump and refrigerator have the same equipment, the same concept. The only difference is in the desired output. For the refrigerator, the desired output is QL. However, for heat pump, the desired output is QH. If you use the definition for the efficiency, then you can prove that the COP, the coefficient of performance for heat pump, can be determined from this equation. If you compare the COP of heat pump and refrigerator, you can prove that there is this relationship between heat pump and refrigerator COP. Then we discussed the Clausius statement for the, the second thermodynamic law. Simply based on the Clausius statement, if you want to transfer heat from a lower temperature medium to the higher temperature medium, you need to consume W. Or, you can actually use, this, actually a statement. So, but keep in your mind that, simply if based on the Clausius statement, if you want to transfer heat from a lower temperature medium to the higher temperature medium, you need to actually consume W. Then we discuss reversible and irreversible processes, and then keep in your mind that all processes in, real engineering are irreversible process. Now, in this part, guys, we are going to discuss the Carnot cycle, which is totally reversible cycle. What's the benefit of a study of this reversible process? We already discussed it, guys. The first thing is that it's much easier to actually study or simulate the reversible processes. And the other thing is that by actually study the reversible process, we are able to provide an upper limit for the performance of real cycle. So in this part, first, we studied the reversible process for heat engine. So the reversible process for heat engine is called the Carnot heat engine. Carnot heat engine actually has 4 different steps. 2 steps or 2 processes are isothermal and 2 processes are adiabatic. If you remember, guys, for the heat engine, we have actually 4 different processes. The first process, heat absorbed from a high temperature source, and then the second one, there is a turbine, so we have an expansion, and then W produced, and then there is a compressor or constant actually temperature, a heat transfer to the sink, and then the last one is that actually the pump. So here you can see the different steps for the Carnot cycle or different processes. So keep in your mind that the Carnot cycle is totally reversible process. So the first one is reversible isothermal expansion. So this process actually is in this actually step, heat is absorbed from heat source. So this is a constant temperature or isothermal expansion. The second one is turbine, or if you remember, it's turbine to produce the W. So for the Carnot heat engine, the second step is reversible adiabatic expansion. So in this step, the third one in the Carnot cycle is reversible isothermal compression. And the last one is the reversible adiabatic compression. So keep in your mind that for the Carnot cycle that work on based on the heat engine, actually we have 4 reversible processes. Now, question: This is a reversible process, correct? The Carnot cycle, the Carnot heat engine. What happened if we just, reverse this process? If we reverse this process and then we start from the point 4 to point 1, then 2, 3, and 4, you can see that this is actually a refrigerator. Correct. So this is called Carnot refrigerator cycle. So the reverse actually Carnot heat engine cycle is the Carnot refrigeration cycle. Now, the Carnot principles. There are two principles for the Carnot, cycle. The first thing is that assume that we have actually, high temperature reservoir and low temperature reservoir or sink. So for any heat engine that work between the same source and sink, all reversible heat engines has higher actually thermal efficiencies than the irreversible processes. This is the first principle. And the second one is that all reversible process heat engines that work between these two heat source have the same the thermal efficiencies. This is called the Carnot principle. We can prove simply the first one. How? Assume that we have a high temperature reservoir at TH and low temperature reservoir at TL, and then there are two heat engines work between these two sources. The first one is irreversible heat engine and the second one is reversible heat engine. Then let's assume that these two actually heat engines get the same QH from this heat source. Now let's assume that the thermal efficiency of a reversible process is higher than the reversible one. So if the thermal efficiency of this irreversible heat engine is higher than the reversible one, we can show that the W irreversible is higher than the W reversible, correct? Now, you know that this is the reversible one, so we can just, make it reversible. So if we just reverse this, heat engine, we have a refrigerator. We already discussed it, correct? So now let's assume that we add W reversible, to this refrigerator. Then this refrigerator gain QL from this reservoir and then transfer QH to the this source. So we already assume that the QH is the same for both these cycles, correct? So what we can do, we can cancel this reservoir and then we can directly transfer QH from the reversible actually refrigerator to the irreversible heat engine. Now what happened? We have a device that work actually or exchange heat with a single reservoir and then produce the net work. Why the net work? Because the W irreversible is higher than the W reversible. And this is impossible based on, the second, thermodynamic law, actually the Kelvin-Planck statement. So meaning that the thermal efficiency of reversible process must be higher than the thermal efficiency of irreversible one. Okay, so actually we can use in engineering, normally we use the absolute temperature for calculation. We already discussed it in chapter 1. The absolute temperature in SI system is Kelvin 1, and in British one is Rankine. So it's possible to show that the QH over QL for reversible process, this ratio equals to the TH over TL. Keep in your mind that the temperature here must be absolute temperature, either Rankine or Kelvin. Now, the Carnot heat engine. Okay, so look guys, to calculate the thermal efficiency of heat engines, either reversible one or irreversible one, you can use this equation. We already discussed it. So this equation is valid for both reversible and irreversible heat engines. For the reversible one, you saw that we can substitute actually this ratio with the TL over TH, and then we can modify, we can rewrite this equation into this format. So keep in your mind that to calculate the thermal efficiency of reversible heat engine or Carnot heat engine, you have two options. You can either use this equation or this one. However, for the irreversible heat engine, you have only this equation. You must use this equation to find the, thermal efficiency of irreversible process. So this equation is valid for both reversible and irreversible. This one just for reversible one. And then keep in your mind that the temperature must be absolute one. Okay, what's the application of this, Carnot heat engine? What you can do, guys, you can calculate the thermal efficiency. Actually, you can use this, equations to just study the possibility of, making heat engine, with different, thermal efficiencies. How you can calculate the thermal efficiency for the reversible process. And also, you can calculate the thermal efficiency for irreversible one by using this equation. So you can calculate the thermal efficiency for reversible heat engine by using this equation, and you can calculate the thermal efficiency of irreversible heat engine by using this equation, and then you can compare these two values. If the thermal efficiency of actually heat engine is lower than the reversible one, this is actually irreversible heat engine. If the thermal efficiency equals to the thermal efficiency of reversible heat engine, then this is a reversible heat engine, and then this is the maximum you know uh, thermal efficiency. What happens if the thermal efficiency of your system is higher than the reversible one? Then this is impossible. It's impossible to make a heat engine, with this thermal efficiency. Okay, so the quality of energy. What is the quality of energy? Assume that we have a heat engine that work actually between a source and sink, and then let's assume that the temperature of sink is constant. What happens if we increase the temperature of source, in this system? Based on the definition for the thermal efficiency of reversible process, if the TH increases, this term decreases, correct? So meaning that the total actually thermal efficiency or this part increases. So meaning that if you increase the temperature of source, correct, the thermal efficiency of reversible heat engine increases. So the higher temperature of reservoir or TH means the higher thermal efficiency for reversible process. Actually, this is valid for irreversible process as well, meaning that the higher temperature of source actually cause to have the higher thermal efficiency for both reversible and irreversible processes. So we can discuss the Carnot refrigerator and Carnot heat pump. So if you remember, we already discussed that, the coefficient of performance for refrigerator and heat pump. So you can substitute this term by TH over TL and this one by the TL over TH for reversible refrigerator and reversible heat pump. And then we can just use these two, correlation to find the COP of reversible refrigerator and reversible heat pump. Again, guys, keep in your mind that you can use this two correlation to find the COP for refrigerator and heat pump for both reversible and irreversible one, but these two equations are just valid for reversible. So you can use this COP to actually as an upper limit for the COP of refrigerator and heat pump. So for this equation, guys, for the COP of refrigerator, what happened at constant TH if you increase the TL? If you increase the TL at constant TH, this term decreases. keep in your mind that the TH is higher than the TL. So normally this term is higher than, 1. If you increase the TL, this term decreases and then approaches to 1. And then this term actually decreases, correct? And then eventually the COP increases. So the higher TL means actually the higher COP for the refrigerator. The same actually, trend for the COP heat pump, you can show it. So again, guys, for both refrigerator and heat pump, you can calculate the COP for the process, and then you can compare with the reversible one. If the COP of the refrigerator is lower than the reversible one, we have the irreversible refrigerator. Equals to the reversible one, there is a reversible refrigerator, and higher than the COP for refrigerator, it's actually impossible to have this system. Okay, so this is my lecture for today, and then I will solve some problem on Wednesday. Thank you very much and have a great day.